In this project, we will numerically validate the data provided by the paper named control of flow past a dimpled circular cylinder. Now, as you can see in this slide, we have extracted the figure 1 of the paper, in which you can see the schematics of the cross-sectional and side views of the dimple cylinder. Now, in the reference paper, several patterns have been considered for the placement of dimples on the cylindrical surface. In present work, the DF type pattern has been used. This means that the dimples completely fill the surfaces. The main purpose of this work is to investigate the aerodynamic forces, including drag and lift force, on the outer surface of the cylinder, and also to calculate drag and lift coefficient. As was mentioned in previous slide about validating the paper's results for the lift and drag coefficient, we have brought to you two graphs where you can compare our CFD simulation results with the papers. Under the General Setup tab, you can see different buttons from scales to units. By clicking on a scale, a new window will appear showing you the domain extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now, in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. Now, there are several assumptions taken into account in this project. The first one is that the type of our solver is set to be pressure-based since we are dealing with incompressible flows. Also, as for the velocity formulation, we have taken the absolute formulation for this. And as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. After double-clicking on the viscose button, a new window will appear. In the appeared window, you will see that we have chosen two equations, standard K epsilon, to solve for our fluid flow. The standard K epsilon model is one of the most renowned models for solving the turbulent fluid flows, and actually two equation K epsilon model allows the determination of both a turbulent length scale and time scale by solving two separate transport equations. Now, after expanding the fluid section under the materials, you can see that water and liquid material have been added to this project. In order to add a new material, you just have to right-click on fluid and then select new. After doing that, in the appeared window, you either can define a new material by defining its properties yourself, or you can click on Fluent Database button and then select from the available list of materials in the software. Now, under the cells and conditions section, all you have to do is to assign the water liquid material to your computational domain. To do this, you have to just double-click on the float, and then in the appeared window in front of the material name section, select water liquid material. After clicking on the inlet boundary, you can see that the type of this boundary is defined to be velocity inlet. By clicking on Edit button, a new window will appear in which you can change the settings for this boundary. As you can see in this window, the velocity magnitude defined for this boundary is equal to 0.45 meter per second. And as for the outlet boundary, you can see that the type of this boundary is defined to be outflow. Now, outflow boundary condition is used when we do not have any idea about the pressure or velocity of the fluid flow in that section. Now, as for wall boundaries, by clicking on each of them and then click on Edit, you will see that the stationary wall motion and no slip shear condition is defined. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first-order advent and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. We may also change the under relaxation factors. These factors may be between 0 and 1. Based on the simulation and the project we are doing, we may change these under relaxation factors. But remember that the values set in here are the recommended values for the project, and we highly recommend you to not change these values. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing the 0, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on a arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. Now, if you expand the report definition section, you can see that two reports have been defined. The first report, if you double click on it, you can see that a new window will appear. In the appeared window, under the report output tab, you can see that a lift coefficient report on the dimpled cylinder wall has been defined. Also, when you double click on the second report, you can see that a drag coefficient on the cylinder wall has been defined. Also, in order to define these report types, just have to right click on report definitions and then going over the new, and after that going over the force report, then you can see that drag or lift or moment or force reports are available. After double clicking on the residuals button, a new window will appear. In the appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now, in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. After double-clicking on the Run Calculations button in the Appeared section under the Parameters part by just defining the number of iterations and then clicking on Calculate button, the software will start the simulation process. Now, in order to define a 2D contour, we first have to define a new surface or plane for our geometry. To do this, you have to just right-click on Surface and then going over to New and then selecting Isosurface. Now, in the Appear window, say we want to generate a surface in the middle section of our geometry, which would be in Z direction. And for that, under the surfaces of constant, we select Mesh and then Z coordinate. After that, we click on Compute button so that the software will calculate our geometry extents in Z direction. After that, by going under the ISO values and then selecting this specific value, we will generate a surface exactly in the middle of our geometry. In this section, in order to extract a 2D contour, just have to right-click on Contours button and then select New. After that, in the Appeared window, under the Contours of section, you can select between the desired variable. For example, in this case, we have selected pressure. After selecting the variable, we go under the Surfaces section and select our desired surface, which would be the surface that we had defined in previous slides. After that, by clicking on Save or Display button, the software will give you the 2D contour. Now in this contour, you can easily see the pressure distribution around our dimpled cylinder. Also, you can see the stagnation point in front of the cylinder where it has the maximum pressure. In order to extract a different contour, you just have to change the variable, for example, from pressure to velocity, and after that, just by clicking on Save or Display button, you can see the velocity 2D contours. And in this slide, you can see the 2D contours of velocity and the wakes that have been generated behind our dimpled cylinder. Now, as was mentioned earlier in previous slides, we had defined two different reports. The first report was the lift coefficient and the second report was drag coefficient. We're going to use the amount for each of these reports in order to validate the data provided by the paper. Now, in order to obtain the value of the lift coefficient, just have to double click on the report and then in the Appeared window, click on Compute button. After that, in the Console tab, you can see the value of the lift coefficient. Just as was explained in previous slide, just by following the same step, you can obtain the value of drag coefficient. Now, as was mentioned in previous slides about the purpose of this project, which is to validate the results obtained by the paper for lift and drag coefficient. After calculating the values of lift and drag coefficient in our CFD simulation, you can easily compare our data with the papers, and then you can see that we have validated the data obtained by the paper. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide. To benefit from MR-CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.